Let's start the lecture. So, what did we discuss in the last lecture? A lot of people have already got the 15 classes, is it? I see less people here. Attendance policy, you just need 15 classes of attendance, right? So, a lot of people have already got that, is it? Yeah. So, what did we discuss in the last lecture? Hmm? Policy graded. So, what in that? So, what are the different kinds of policy gradients we discussed? Huh? Yeah. So, we discussed reinforce. Then we discussed this concept of baseline, right? Then we also discussed what is called actor-critic method. In today's lecture, what we'll see is we'll look at uh, a few more variants of actor-critic algorithm. One version is called A3C and A2C, and uh, there is something called generalized advantage estimation. So this is also something which we'll discuss. So what was the definition of advantage function? Do you remember? So what did we define as the advantage function? So all of you are doing projects, is it? So you don't have to do anything for NSM, is it? So what is the advantage function definition? Maybe in the third assignment I'll give some theory questions. Okay. So, so what is advantage? We define it as A of ST comma AT, right? AT of advantage is a function of state comma action, which is defined as Q of S comma A minus V of S, right? So V pi of S is the value for being in state S. If you are in state S and follow policy pi, what is the value that you will get? This is what this is. In the current state you take an action A, and from the next step you follow policy pi. So this is called the advantage because if you had followed policy pi, you will get this much. But in this current state, you have to action A. So how much advantage do we have versus a typical action that you would have taken with respect to policy pi? This is the thing you'll get if you take some action according to policy pi. For deviating from policy pi and taking another action A, how much advantage do we have? Okay. So if the advantage is positive, maybe that means that you should increase the probability of taking action A, right? Because A is a good action, right? If this turns out to be negative, maybe then A is not a good action compared to the current policy, right? If we're deviating from the current policy and taking action A in the status, whether it is good or not, like how much advantages is it? Okay. So, in today's lecture, we'll discuss what is called generalized advantage function, which is like we have looked at what is called uh, eligibility traces, right? Do you remember what are eligibility traces? One step one step return, two step return. Do you remember all these things? One step TD, two step, n step TD. So while so you can think of this as you're subtracting a baseline of v pi of s from q pi, right? That is one way to interpret this. So one more thing is this generalized advantage action, this generalized advantage estimation is this concept comes from the concept of lambda returns like that you have. Like instead of using, for example, when one of the student asks how whether if you want to implement this in your policy update, whether we should maintain separate Q network and separate value network. Like we are maintaining one policy network, right? Which is parameterized by theta. We are updating the thetas. That is one thing. And if you want to use this in your gradient estimate, then you have to maintain some value network for the Q, one value network for the V, right? Instead of doing two separate value networks, one for Q and one for V, we discussed one way to just do with one value network. Do you remember what is that? What is it? Huh? Yeah, we could approximate Q pi using V pi, right? How? We can roughly write it like RT plus 1 plus gamma times V pi of ST plus 1, right? We can write Q pi of ST AT like this, right? It's a rough way of writing Q pi of ST AT. So if you write like this, then you just need one network, right, for the values. Because if you just maintain the value network corresponding to V, then you can estimate both these things, correct? So here we are using a one-step approximation for one-step bootstrapping for Q, right? We what else we could have done for Q here? We could have done RT plus 1 plus gamma times RT plus 2 plus gamma square times V pi of ST plus 2, right? That is also one way of approximating Q. So if you do that, you will get some other method. And there will be a lot of such possibilities, either one step return, two step return. So if you combine them using some approximate, like some appropriate probabilities, 1 minus lambda, 1 minus lambda into lambda, etc. Like then you will get what is called a generalized advantage estimation, which we'll look at in detail. But that is one variant which we'll also see in today's lecture. So instead of using this q pi minus v pi, we can use these kind of returns. Like there are multiple returns that are possible. You just take an average of all possible returns. Okay, so that is about generalized advantage, generalized advantage. And A3C is called asynchronous advantage actor-critic. Okay, and A2C is just advantage actor-critic. Okay, so that could you can think of it as synchronous advantage actor-critic if you want. Okay, so these are few concepts which we'll discuss in today's lecture. Hmm. So before I go into the specific details of these, let's briefly recap what we know about the policy, uh, the basic policy gradient algorithm. So what is the basic policy gradient algorithm? What is the gradient? What is the performance metric? Do you remember? If phi theta is a policy which is parameterized by a theta vector, what is the performance metric of this policy? How do you measure how good is that policy? Huh? K pi? No, right? You're not talking about the gradient, you're talking about the objective which we want to. You remember we discussed like this, right? We had some starting state distribution and we measure the This is what we wanted to maximize, right? This is the value of that particular policy. If you start from state S naught, but you might start from some random state according to the distribution D, and this is the objective we had. Okay. This is the third time I'm telling this. Everyone is blank, as if they're hearing some new thing. Okay. So what did we write? What did we get as our gradient? Do you remember? Yeah, we have derived multiple versions. Like one is you sample the trajectories according to pi, where tau is the trajectory. You sample the trajectories according to tau, and what is the term inside? G of tau into del log pi theta of at given st, right? So this is our thing. Then what else we did after this? This is the first thing we derived, where G of tau is what? G of tau is the total return that you get, is the return that you get from the starting state. Like tau is what? Tau is the path. S naught, A naught, R1, S1, so on, ST. So tau is a trajectory which starts from state S naught. And if you are given all this information, you can calculate what is G tau, right? What is G tau? R1 plus gamma R2 plus so on, appropriate power of gamma power RT. Okay. So this is how we started with. Then we have derived some variants of this, right? Instead of G tau, we made it GT, right? How? How did we do that? Because G tau is a function of all the returns. Instead of that, what we did was we use this concept of baseline. What does baseline tell us? If I have something like this, like mm, so, so for baseline, what did we do? We showed this particular thing, right? If there is some B which will have this property. If there is any baseline B which will satisfy this property, then we can subtract this from G tau, right? Because if there is any B which will satisfy this property, then if you subtract that from G tau, then the gradient will not change, right? Because if I just subtract this and write it like this, then you can just take the B outside, and that thing will become 0. So we have discussed that any B which is not a function of AT we can use, right? The good thing about that using some baselines like that is you will have faster conversions, the variance of the algorithm, and there will be some faster conversions. So finally, what we derived one expression for this, and based on that expression, we derived multiple variants of the policy gradient method, right? What was that generic expression? Gamma power t into q pi of STAT del theta log pi of AT given ST, right? This is if you are not able to remember all the things, you can just keep this in your mind. Okay. Huh? Okay. Okay. So for any variants of policy gradient descent, you can start from this expression where you have this kind of a thing, and if you want to write it more betterly, maybe you can think of it like this. You can also subtract the baseline if you want. Okay, because you can subtract any baseline which is not a function of 80, then we'll still have the same expression. Okay. So what is reinforced according to this thing? For getting reinforced, what should we do in this? You take b equal to 0, you don't have any baseline, and what else? What else we should do to get reinforced from this? Just take q pi of STAT. Instead of q pi of STAT, you just use GT. Okay? Because expected GT given STAT is nothing but q pi of STAT, right? So you're just taking one sample from this. Okay? So this is what is reinforced algorithm. Okay? So what you have to just use the gradient will be GT gamma power T GT into. So this is what you'll use as the gradient. Okay. So what will be our update rule? Theta nu equal to theta old plus some small constant times this thing. Okay. Is this clear? So just to see that in the algorithm form, this is the reinforced algorithm where here what we'll do, we'll first generate one trajectory. We'll first generate one trajectory like this from our current policy parameter. Like you'll start with some arbitrary parameter, right? You'll start with some theta. You just generate one trajectory according to your policy, and then what do you have to do? You have to just compute GT for every t, and then just update your theta. Okay, this is what you're seeing, right? This is like GT only, right? Okay, so is this algorithm clear, everyone? Like all that you have to do is uh, you you can ask me any doubts because this is going to be your third assignment, which we'll release tomorrow maybe. So maybe we'll give you a card pole environment where you have seen what is a card pole environment, right? Where there'll be some pole hanging on some vehicle, and if you keep moving left, your main thing is you have to balance the pole, right? So that is what we'll give for you in the assignment. So all that you have to do is you start with some arbitrary parameters and generate one trajectory, and based on that you compute your returns, and then you have to do this thing. Okay. So depending on what policy you take, you'll have some derivative with respect to this. So what is some policy? What is some policy that you can suggest? Oh, Phi you have to decide, right? Because phi theta is some hyperparameter which you have to decide. So what functions? For example, in the card pole, we'll have these kind of. So the card pole, if you recall, there will be something and there will be a pole, and you have to keep balancing that pole without falling down. Okay. So, for example, the card pole environment has four state features. Like the state, we have to write in terms of some features, right? So the state will be represented using some four features: h1, h2, h3, h4, which are some real numbers, which corresponds to these four properties of the state. So where is that pole right now? Like maybe it's like it's in this axis. Where exactly is that? What is the card position? That is one parameter, one feature, and what is the current velocity of the card, and what is the current angle of the pole, and what is the angular velocity of the pole. So you represent the state of this card pole using these four features, and the actions will be, for example, if the pole is right now, if the pole is if the pole is in this position, what is the right action to take? You have to move right, to balance the pole. So based on the position of based on this feature vector, you have to decide whether to push the card to the left or push the card to the right. Okay. So you have two actions. One is the left action and the right action. Okay. So for this, let's say this is a problem which you have to solve. What is one way to model your policy? What is the basic way that you can think of? So your policy should be a function of what? Your policy should be pi theta s of a given s, right? S is what for us here? S is a real vector of length 4, right? So, and what can be some basic function that you can think? So, maybe one way to do that is maybe, let's say, for left, you model some probability parameters, and for right, you model another parameters, let's say. Okay. So, what can be my, for the left action? This is just like your contextual bandits, right? If you remember, you can think of each action as an arm, and the state is a contest for you, right? So in the contextual bandits, what did we do? We modeled it as a linear function of the state features, right? So that could be one way of doing it. For example, you can do it as theta, let's say theta left h1. I'll just call this h1. Maybe I'll write it neatly somewhere. So the probability, let's say instead of modeling, let's say the probability of taking left given your state vector h. Okay, I can, for example, write like this. Right. So it will not be exactly probability. Maybe let's call it the some function of, this is the weightage that you give for left. Let's say this is proportional to this. Okay. Or you could also use softmax if you want. You can raise it to the power of this, and you can also do something like this, right? Similarly, e power theta 1 right h1 over h2 plus theta right. Okay. This is, so what will be the probability if I model the function like this? It will be the ratio, like this is like the log likelihood. You just have to, if you want, if I call this, if I want this, what will that be equal to? right? This will be the probability, right? Because these are proportional to these two terms. So you have to normalize it so that it's equal to 1, right? The probability of left and the probability of right should be 1. Okay. So this you can take as your policy if you want. And after you take this, you know how to take derivative, right? You just have to take, you have to just take derivative of del log phi. Because our derivative is, for example, in the reinforce, what is our derivative? Gamma power t into gt into del log phi of at given st. You want something like this, right? You just take the derivative appropriately, and then you compute this and keep updating your policy. You just generate one sample episode and you calculate the derivative for this and keep updating this. Okay. Uh, so this is the basic version of reinforce. Okay. So what is reinforce with baseline? What can we do for that? Huh? If the number actions are continuous. So you need not have separate parameters like this. You can have parameters for the action as well. So for example, I can have action parameters. Let's say for this case, the action can be, let's say I call this as left and right I call this as 0, 1. Now I'll just take my s comma a equal to x1, x2, x3, x4. I'll just call this a1, a2. I'll just call this a1, a2. And I can have my policy to be just some theta transpose. Uh, I'll just concatenate this and call it something. I'll call this as my x, let's say. Right? This whole vector I can treat it as my representation of the state and action. And I can just write phi of a given s is this theta transpose this vector. Okay. That is one way of doing it. You can come up with whatever ways you want. You just convert action also into some real number because that's continuous means it will be in real number, right? You just take whatever function you want. Okay. So this is about reinforce, right? What is reinforce with baseline? So what baseline we have suggested? Do you remember? So if you remember, for example, in the bandit setting, what did we suggest? Like instead of using RT, what did we suggest as a baseline? RT minus R bar, right? R bar is the average reward that you got till now. So similarly, for this also, there could be two ways of. Generally, there are two popular baselines which are used. One is you subtract GT minus um, R bar, which is the average reward that you get. That is one thing you can do, but more popular is this thing. You subtract the value of that thing. Okay, this is like the advantage, right? GT is like the q pi, and you're subtracting the value of that thing. So this is telling how good is this action compared to a typical action. You got GT for taking some particular action 80 at that state, and versus what is that you would have got if you had followed just policy pi. Okay. So what will be the only difference in the algorithm? So instead of using GT, you have to use this thing. So what will you have? You have gamma power t into del log phi of, right? Previously we have used GT, now we are using GT minus some baseline. The baseline is the value function of that current state. Okay. So who will give us the value function? GT, how do we get GT? We just run one episode using our current policy pi, then we'll get GT. Then what about V hat? How do we get V hat? We have to model it as another function and estimate that weights W, right? So we have some parameters theta for the policy. Similarly, we have some parameters W for the value function. Okay. So what can be one value function for, let's say we are doing with the card pole environment? What can be one simple value function? W are the weights of the value function, which you have to learn. Parameters of the value function. So what is the simplest value function that you can think of? Yeah, again you can use the linear value function, right? H1 W1 plus H2 W. As we use, I've seen cardpole has four state features, so you could use this value function, right? And you have to learn these four parameters which are unknown for us, right? So if H is the state features. Okay. So we know how to update our theta, right? If what is the update for theta? Theta nu equal to theta old plus alpha times this thing, right? That is clear, right, for us? Theta nu equal to theta old plus some alpha times this thing. That is how we'll update our theta vector. We just run one episode and then get this GT and then do this. Then how will we update our W? So we have to learn W also, right? If you use some arbitrary W's, then that won't represent the value function, right? So what did we learn in the function approximation for the value function? We have to minimize the loss function, right, for W. What is the loss function that we generally use for the value function? That is V pi hat of HW minus V pi of H, which is the true value function square, right? We want to find the W which has the best, least possible error, right? Over all possible states, right? So how can we do this gradient descent? What will be the gradient for this? So that will be like if where you can think of this as expected value of the probability of being in some state S when you follow policy pi. Okay. So this will be what? W nu equal to W old plus some alpha times. What should we write here? V pi. So you have to minimize this, right? Right? Should it be minus or plus here? Should it be minus or plus here? Maybe that is okay because we want to go in the opposite direction of the gradient. This is one term, and then we'll also have this, right? Is this clear? You're just taking the derivative of that. Like there could be two also, but you can observe the two into the alpha because alpha is some arbitrary constant. You can just think of that two into the alpha. Is this clear? But what is the issue here in this? Huh? We don't know what is v pi of x, which is the true value. So what can we substitute here? We're anyway running one episode, right? So we can use what here? GT instead of v pi of x, which is like the Monte Carlo based function approximation, right? Is it clear? Because what will we do? We'll start with our current policy. We'll run one episode. We'll get all the rewards, right? Then we know the GT starting from every t. So then we can just use this gradient there. So instead of v pi, you use GT there. Okay. Rest of the things we know, right? Because we know what is this. This is our v pi. We can calculate what is this. That will be just the feature, right? If you the gradient of this will be nothing but the feature vectors because it's a linear function. So the gradient will be just h1, h2, h3, h4. Okay. So now you understood what is the algorithm with reinforced with baseline. Okay. So let me show you the textbook code so that pseudo code so that you are comfortable. Okay. So this is the pseudo code where you start with some policy function. For example, for the card pool, we have started with the soft match function where we have used soft match linear plus soft match, right? We use the theta transpose x, e power theta transpose x, which is proportional to the e power theta transpose x. So you'll start with some arbitrary policy function. Then you'll start with some function for the value. Like for example, we took the value function to be this. And our policy function, if you remember, this is our policy function. This is our policy function. We'll start with those two. And then you initialize, there'll be some step sizes corresponding to both the value update and the policy update. You can choose some small numbers or you can use some numbers which decrease with time, like 1 by t, something like that. And you have to initialize the policy parameters and the value parameters with some arbitrary values. Maybe you can start with 0. Then what you have to do with your current policy parameter, you just generate one episode. From that episode, you calculate what is GT. For every T, you're doing this. You calculate the GT for every possible T. Then what is our update rule for this? This is, they're calling this as delta. They're calling this difference as delta. Okay, the delta is the difference between your estimate and the GT. So that they're calling it as delta. And then this is the update rule for W, right? You just update it. And then this is the update rule for your policy, right? This is delta is what here? GT minus V pi hat, which is the baseline version of this thing. That's what we have seen, right? This is delta, right? So this is like gamma power t into delta into del log pi of at given st. So that's what they're doing here. Okay, gamma power t into delta, which is the difference between GT minus V pi hat, this thing, and then you are doing this. Okay, so this is the reinforced with baseline. So is this clear? Yeah. No, we are updating W after that. So you're saying can't we interchange these two steps? Huh? Yeah, within this, it is within this loop, right? So for every step, like first you generate the whole episode and then you run this for each step in the episode. So the W is getting updated and in the next calculation of delta, it is being. Okay. So any doubts in this part? So you don't need any base code, right, for the assignment 3 part A. You understood clearly what to do. So these are the two things you have to do in the assignment 3 part A. Okay. Which is you have a card pole environment, you have 4 features, you take linear policy like e power uh, theta transpose x as a policy, like proportional to that as a policy, and you take a linear value function and just write the code for this algorithm. Okay. All that you have to do is take derivatives and just do this. You just generate one episode and do this. Okay. So any doubts before I proceed further? So maybe I'll show you one graph, which is so I'll just show you one graph, which is a comparison between with baseline and without baseline. What is the performance difference? So uh, this is not an card pole, but some grid kind of an environment. They're comparing the difference between the reinforced with baseline and without baseline. Okay. So as you can see, the reinforced with baseline will converge somewhat faster, like to a good reward. Okay, compared to the reinforced without baseline. The reinforced without baseline will also reach that value, but it will take some more time. Okay, so this will help in the conversion speed of the policy. Okay, so you have to generate this kind of a comparison for the card pulling. So now this is about the second variant. Like you started with reinforce where you just use GT instead of the Q pi of STAT. Then we use GT minus V pi. That is the reinforce with baseline. Then what is the other variant? So what other variants we have discussed? Reinforce with baseline, actor-critic, right? So it's I'm like just recapping the last lecture still, right? That's why you're not so enthusiastic, is it? Because I'm repeating. Okay. So this actor-critic, what do we do? So this is the gradient, right? We had this term in the gradient. In this term, when we use this as GT, we get reinforced. When we use GT minus V hat, V pi hat of SW, we get the reinforced with baseline. Now what should we do instead of these two? So we will use the cube of, if you just use Q, some estimate for, if you just use some estimate for Q pi, then substitute that instead of Q pi, that is also an actor critic algorithm, right? Because here we are just taking one sample return and using that as Q pi. Instead of that, you maintain some estimate of your q function and substitute that q function estimate instead of q pi. How you can learn this q function estimate? Similar to what we have done in the value function, right? You just take some formula for your q pi of s comma a with some parameters, and you keep learning that using this mean square error minimization. And instead of v pi, like wherever you had q pi, instead of that you can use gt kind of an estimate. So that is one basic version of Actor-critic. What else we can do? Just like instead of gt, we substituted q pi hat of STATW. What is the other variant that is possible? Add a baseline to that. So what will be that? Q pi of STATW minus v pi of ST. You could have different parameters if you want. Maybe what should I write for parameters? Maybe Z or some parameters you can have if you want. This is one way, but generally it is not done like this. Instead of that, as I said, instead of using this, what do we use? You just approximate this as RT plus 1 plus gamma times V pi hat of ST plus 1 W minus V pi hat of ST W. Okay. So if you use this instead of Q pi in this thing, that is what is Actor-critic with baseline. Right? Is this clear? So one good thing about this update is the previous two, the reinforce and the reinforce with baseline, are offline methods, right? Because for calculating GT, we had to run the whole episode and then you have to update your theta. But what about this thing? For calculating this update, all that you need is RT plus 1, right? So this is an online method because we are using bootstrapping. What is bootstrapping? You estimate your current value based on the next state value, right? So here, this is bootstrapping, right? So you understand, right? This is an online method because all that you need is RT plus 1. After every step, you can update your RT plus 1. So the algorithm will be more or less the same. You just update your theta new equal to theta old plus some gamma power t into this term into the del log pi. That will be your update rule for theta. And what will be your update rule for v pi? What update rule we should use for v pi? Do you want to use this update rule? Do you want to use the same update rule for W? We can, but would you like to use that? What is the problem if you use this? Because we just got a benefit of online algorithm, right? Because it was only dependent on RT plus 1. So then if you want to use this update rule for your W, then you'll lose that benefit, right? Because you need G for this. Then what else you can do? This is Monte Carlo based function approximation. Instead of that, you use TD based function approximation, which we have discussed before, right? So what is TD based function approximation? Like you'll have the same thing, like this is Monte Carlo based function approximation where you use GT. Like this is the same loss function, you'll have the mean square error, and instead of V pi, you use GT here in the Monte Carlo function approximation. In the TD based function approximation, what will we use instead of V pi? You can do this, right? Like the rest of the part will be same, except for this part, you'll just use RT plus 1 plus gamma times V pi hat of ST plus 1 W. You just take one action with respect to your current policy, pi, and then the remaining return. Okay. That's the only difference. Instead of, if it is a Monte Carlo based function approximation, you replace the true value with GT. If it is TD based function approximation, you replace the true value V pi with a bootstrapped version of your return, which is RT plus 1 plus the remaining. So these are the only two changes that you'll do. Okay. In this theta update, instead of using GT, you'll use a bootstrapped version of the return, which is RT plus 1 plus gamma times V hat of ST plus 1. Similarly, here also for W also, you will just use a bootstrapped return. Okay. So let me show you that algorithm in detail. Okay. So as usual, we'll start with some function approximation, whatever we want. For example, a linear plus softmax, maybe a linear function approximation for the value function. But in general, you'll use some neural networks. But for this course, we can use the linear function. Okay. Maybe if you want to do deep RL, you can use deep neural networks, which takes a ST as the input and gives V pi as the output. Okay. Then we'll same thing like the same here. It is same here. You will initialize with some random weights, initial weights, and then what you'll do, you are looping over multiple episodes, and for each state, like you can clearly see that this is a online algorithm, right? Because previously, what was the first thing we were doing? We were generating one full episode, right? For the reinforce with baseline, etc. First, we generate one full episode, and after that, whatever updates you are doing based on the GTs that you get. But if you look at this thing, you're just taking one action A according to your current policy. Then you are observing what is your next state and what is the reward, and immediately you are making some update for your theta, right? So this delta is what? This is the advantage, right? This is the thing we use for advantage, right? Because Q minus B was our advantage, and Q we wrote it as R plus gamma V of S dash. So that's what we have here. Like this is the RT plus 1 plus gamma times V of ST plus 1 minus your V of ST. So this is your delta. And this is the only difference. Like after every step you are doing this update in the episode, you are not waiting for the whole episode to end. After every step in the episode, you calculate this delta and you update your W and theta. Okay. I think they wrote this in the vector form. That's why they are doing these kind of things. But if you write the scalar form, you need it for you. Okay. So this is the actor-critic algorithm with the baseline, where the baseline is your V pi, right? So if you want actor-critic without baseline, what is the change that you have to do in this? Huh? So you don't subtract this thing here while updating the this. Okay, that's the only thing. For the theta function update, you don't subtract the baseline, which is your V pi hat. Okay. Or you could directly learn the Q function instead of learning a value function. That is also. Okay, so this four or roughly reinforce is like a Monte Carlo based policy gradient method, because we are running the whole episode and then doing something with the GTs. So I can think of reinforce as Monte Carlo based policy gradient method, and reinforce with baseline is like the baseline version of that. And then actor-critic with the baseline is like the TD version of that. So you can think of it as a online algorithm, because after every step in the episode, we are able to update our theta parameters. So, like all the advantages of online methods will come in. For example, if it's a continuing MDP instead of an episodic MDP, you cannot use reinforce, right? Because in a continuing MDP, there won't be any terminal state. Like you will keep continuing forever. So your episode will never terminate. So you cannot use reinforce, but you can use this actor-critic method. Okay. So this is about the uh, uh, reinforce with baseline, and actor-critic. Now, whatever I wanted to cover today, those are starting now. Okay. So what are the things I wanted to cover today? I wanted to cover what is A to C, A3C, all that, and GAE, right? So maybe I'll roughly cover these two. So I- in this reinforce with in this A3C, what we'll do is, instead of like you have some, let's say, some parameters theta right now, and we want to update it to some theta old to theta new, right? We want to update that from theta old to theta new. So now there is only one uh, uh, process, one algorithm or one process who is doing this. Like it is generating some it is generating some episode, and based on that it is updating its policy parameters and the value parameters. Instead of that, if you want to do this what there will be some multiple work workers. Like this is a parallelized version of your actor critic algorithm. Like instead of doing sequentially, because it will take a lot of time, because you have to generate one episode, learn from that, and then generate the next episode and learn from that. Instead of some, for some complicated environments, if you do like this, maybe it will take a lot of time. Okay. So to one motivation for doing this parallelized version is to speed up the training time. Okay. So what you'll do is, you maintain something called local workers. So you maintain some three parallel, let's say three workers. You can think of each worker as some parallel environment which is running. Okay, you can think of this as three processes in your program, and each process will take the same environment. And what it will do is, it will take your current parameters. So everyone will copy this theta old. Okay, each of these three workers will copy this theta old parameters, and now they'll parallelly generate one episode each. So each uh, local worker is like a it's like a multi-thread processing, where you just give the current parameters to all these three subroutines, and each of them will generate one episode. And based on that, they will update. One way is they'll just generate one episode each, and they'll send all the three episode data to this original process. Okay. Yeah. So, like, I'm just telling what is the concept of parallelism. Like here, what you'll do is, you'll just uh, like maybe you can keep some threshold for how many steps you want to update. Like even if it's online. So what you're doing is, you are giving your current copy of the policy to three threads, and each of them will generate some experience. One way is they'll give all the experience back to the original process, and now the original process can update the theta parameter based on all these three episodes or all these three experiences. Like maybe if it's not a full episode, let's say you run it for some few. particular time steps. They can give back all the trajectories, and based on that, you can do this. So, for example, our algorithm has this kind of a property, right? Expected trajectory sample from a tau and some function of it, some function you have inside this, right? So when we are doing stochastic gradient descent, what we are doing is instead of we're just generating one episode and taking roughly f as our gradient, right? You just sample one trajectory and taking this f as your gradient, f of tau as your gradient. So instead of that, what is a better estimate of this gradient? You generate three trajectories, f of tau 1, f of tau 2, and f of tau 3. You calculate these three and take the average of these three trajectories. Then that will be a better estimate of this, right? Do you understand what I'm saying? Like we had some particular thing, right, which is g tau into, let's say, t equal to 1 to t log del log y of at given st. We had something like this as our gradient. So what we are doing is we are just sampling one trajectory and we are computing the in inner part of that for that one particular trajectory and using that as our gradient in the SGD. So instead of that, now what we are doing is we are generating three trajectories from the same policy because they are copying the theta old. All the three workers are copying your current theta. That is, they know what is your current policy. So with your current policy, you generate three trajectories, tau 1, tau 2, and tau 3, and then calculate this function for whatever tau they have. And if you take the average of these three f's, then that will be a better estimate of the expected value, right? Because instead of just relying on one sample, now you are relying on three samples and just taking the average of these three as your approximate gradient. So just like a stochastic gradient with a more robust estimate of the gradient. Correct? Any doubts in this thing? So you have you are doing some parallel processing where everyone is generating one trajectory and you use all the three trajectories to compute a better estimate of your gradient. So that's why this will have a lesser variance because the variance from, and here you are just estimating what is an expected value of something. If you use more samples to estimate the mean, then you will have a lesser variance, right? Your approximation will be better. So this will help in improving the variance of your algorithm and help in faster conversions also. Okay. So at a high level, this is the underlying principle in this A3C, etc. Now the question is whether you want to do it in a synchronous way or an asynchronous way, right? Right now you have some theta old. You give this theta old to all these three workers. Now every worker might have different. Every worker will see a trajectory. They might take different times to compute that. So you wait till all the three workers finish that thing and return back the values, and then update your theta. That is called the synchronous version, where you just give to all, you give some work for all the three. You wait till everyone finishes, and then once they return you the values, based on that you update your parameters. That is a synchronous version of this. The asynchronous version of this is whenever anyone finishes their work, they will give their thing, and you just update your policy based on that. So as and when some worker finishes, you take the data and update it. Okay. So here there will be some issues because let's say the first worker finished the work and gave you some information. Now your global parameters theta will change. But after that, the second worker finishes his work and gives you some information. But that trajectory was not calculated according to your latest theta because you already updated your theta from the first worker information, right? So there could be some synchronization issues with this, but it is also known to work fine. Okay. So A3C is the asynchronous version of this algorithm, and A2C is generally referred to as a synchronous version of this algorithm. Okay. So maybe I'll discuss what is GIE in the next class. These two concepts are at a high level, they are clear, right? You're just doing some, huh? Yeah, yeah. So that's what I said. That's what, right? Synchronous version is called A2C. Asynchronous version is called A3C, where you don't wait for all the three to come. Whichever comes first, you use that, and then you use next one later. Okay. So I did not go into specific details, but at a high level, this is what A2C and A3C means. Okay. Thank you.